this function does a couple things. This function decreases and then increases. Is that okay? Does that make sense? The function decreases, then increases. As a matter of fact, let's see. Oh, shoot. We could actually name the intervals on which it decreases and name the intervals which it increases. This looks like it decreases on negative infinity to 0 and increases from 0 to infinity. Okay? We could also say something about the slope, and slope relates to whether it's increasing or decreasing, or the rate of change. As a matter of fact, what would you say, now it's not like the slope of a line, so it's a little hard, but what would you say about the slope maybe like between these 2 points? Positive, negative, or 0? Negative. All right. How about the slope between these 2 points? Positive, negative, or 0? Slope between these 2 points? Okay. If you had to, could we approximate the slope here like, I don't know, negative 4, and the slope here at maybe, hi, how are you? Maybe negative 2, the slope here at maybe, I'll say negative 1. What about the slope right down here? All right, good. Give me one brief second just to say hello to our visitors and tell them what we're doing. Okay. Hi, welcome. This is it's a pre-calc class, and it's juniors and seniors, and we just finished sort of going over homework and having some interesting conversations about homework. Hey, come on in. Having interesting conversations with the homework, and we're going to now talk about a property of function called concavity. So we're exploring it a little bit, looking at graphs, and then we'll probably take a look at some classwork problems. All right, so we said that if the slope is negative, it means the function's decreasing. Does that make sense? If the average rate of change is negative. And hey, what happens after 0? Well, what about these 2 points? What's the slope here? Maybe around 1. Like, can you see what's... All right. So when the slope is positive, or the average rate of change is positive, the function's increasing. When it's negative, the function's decreasing. Fair enough? There's another property that this function has. Because the slope, not the function, be very careful, because the slope is always getting bigger. Can you see that the slope is always getting bigger? No matter what, right? The slope is always getting bigger. We say the function has a very special property called related to its concavity, and we say that this function is concave up. Yeah, so if I had to describe it in words, I would say the function is bending upward. It's smiling, right? That's what concave up looks like. What concave up means is that the slope is getting bigger and bigger and bigger. So in this case, the slope starts off negative and gets more and more positive. Did you have a question or were you stretching? Okay. Alternately, if I take a look, let's see, at a graph like this. It's frowning, so just intuitively, without even looking at the slopes, if I had to ask you if this function's concave up or concave down, you would say, this is definitely concave down. And if we did look at the slopes or the rates of change, we might say that the slope here is, I don't know, 4. I mean, could you see we could do the same thing? 2.
Is it this thing where you always read it
left to right? Definitely. Okay?
You gotta write to left.
And can you see here that the slope is getting smaller and smaller? It actually starts off at 4, which is a positive big number. And as we read left to right, it gets smaller and smaller, more and more negative. And that's the indication that because the slope is decreasing, the function's concave down. And we're actually talking about this in calculus right now. So this is something you'll revisit again next year. And certainly the concavity of a function can tell you interesting things about it. I want to show you a brand new function and talk about its concavity, but before I do it, we should probably see if there's some questions about bending up or bending down, concave up, concave down. You're not yet? Okay, good. But you'll tell me when there is, right? Promise? All right. Thank you. All right. Let's take a look. I think I did. Let's see. Maybe I can do +1. All right. Let's take a look at this function. All right. So this function's a little different. As a matter of fact, let's take a look at average rates. First of all, is the function increasing or decreasing? All the time?
No. Well, yeah. Nothing. That one hits once.
It's probably actually, yeah, it is. It's probably I think it is increasing all the time.
Let's take a look. All right. So Peter says it's never decreasing. The slope's never negative. Now some people are saying what actually happens right here. Is that what the problem is? Because at that point, you're not really getting bigger. But if you go a little to the left of it, the value is going to be a little smaller. So let's see. Let's go back to our calculator. If I trace and I type in, all right, 0, I get 1. If I type in -0.001, I get, no, that's not what I'm supposed to get. I faked the calculator out. That's not good. Those folks at TI.
Mine's really, like, data equals 90.05.
I mean, yours is obviously a very specific calculator question. You can come up after class. We can look at it. Okay. I don't know how to troubleshoot it here and now. Sounds like you're in a different mode, would be my guess. So maybe if you go to mode, you can check that out. So at -0.01, it's 0.9999. At 0, it's 1. Did I increase?
Yes.
All right. And then if I plug in 0.01, I get 1.00001. Did I increase? Yeah, I did. It's increasing. This function's increasing. But that was a good conversation. I like that. So this function's increasing. Let's talk about the slope, though. What would you say the slope is around here? Steep or not steep? Steep. I'll call it 5. The slope here? 2 or 3? I'll call it 2. How about the slope here? It's getting smaller, so 1/2. And then finally, you tell me right here at that one point, the slope is probably around 0, right? Or 0.875. No, closer to 0. Around 0. What would you say is happening to the slope here? 5, 2, 1/2, 0. The slope is decreasing. If the slope's decreasing, the function is? Okay, so when the slope is decreasing, that means that the function is concave down. So for this piece, the function's concave down. Watch what happens now. What's the slope now? What's the slope now? So for this part of the function, let's see. Let's get another color. For the red part, I would say the slope is increasing. If the slope is increasing, what can you say about the function? The function's concave up. So here's an example of a function that's concave down, frowning a little bit, and then smiling for a little bit. Does both.
So how do we
Overall, what would you say it is?
Wait, Sam, go ahead.
Well, how do you indicate that it's happening?
Okay, so if we wanted to say this, we would say, Keith, the function is concave down. on, and I would say negative infinity to 0, right? So I could actually say what interval it's concave down on. It's certainly not concave down all the time. And I could also say it's concave up from 0 to infinity.
And what's 0?
0, it's neither concave up nor concave down. Actually, 0 has a very, very special name. You ready for it? Here it is. 0 is called a point of inflection. And for functions that change concavity, the point of inflection is exactly where it changes concavity. All right. I'll give you a quick... I'll talk to you about hula hoops for a second. Hold on, Evan. If you have a function like this, and this is the hula hoop function, so this is hula hoops that your hula hoops people are buying, right? So it's a fad. So it starts off a little slow, but then it catches on, right? Right? This is how fads work, and it increases very steeply. All right? But then after a while, maybe I should, hula hoops is outdated. Travis, stop pushing buttons. Tamagotchis, did you guys play with those? Right? No, but what, didn't you all have those in lower school? Right? All right. So you had these, and everyone had to have one. But after a while, like a fad gets sort of lame, right? And it levels off. And so people are still buying them, but not as much. Not as high of rate are they purchasing them. So they're still buying them, but the rate's not as much. So this point right here is called a point of inflection, because we stopped from going concave up, and now we're starting to go concave down. And if you're running your business, the point of inflection is really important, because it tells you when to slow up on production. If you keep making Tamagotchis or hula hoops at the rate that you were before, you're going to have warehouses full of hula hoops and Tamagotchis. All right? As a business, you don't want to store items. You want to sell items. So when you can model your sales and you know where that point of inflection is, you still want to make them because people are still buying them, but you don't want to make them as fast. Okay? So points of inflection can be a very important tool to analyze functions, to look at functions when you're analyzing them. All right, Evan, and then talk a little bit more about concavity.
So for the original question of that graph, it's like, is the slope always increasing? Like that was the very first question you asked. That no. Like when you first showed
This one?
No.
Which function are we talking about? This one?
This one. Like the very first thing, when you first put it up, you said, all right, everyone raise your hand.
I said, is the function increasing? Always increasing, not the slope. Is the function always increasing? And the answer here is yes, the function is always increasing. Is that okay?
Yeah.
Okay. All right. There are actually 4 pieces. Here are the 4 pieces. And each of those 4 pieces have different properties in terms of whether they're increasing or decreasing, and concave up or concave down. And to some extent, you can stretch or compress each one of these pieces, and every continuous function is composed of some combination of these pieces, stretched or shifted or what have you. So I want to know, let's see, this will be A, B, C, D. I want to know if it's increasing or decreasing, and then concave up or concave down. Who's up?
Ooh.
Tom, pick one. A, B, C, or D.
Alright, A.
All right, increasing or decreasing? Or concave up or concave down? You choose.
Increasing.
Increasing. Stop. Great, it's increasing. Very good. Calling someone, Tom. What do you want? What letter?
D.
D. Increasing, decreasing, concave up, concave down. What do you want? Decreasing. It definitely is. Good. Calling someone, Monty.
C.
What do you got? That's definitely increasing. Good. Calling someone, Travis. It is. All right. I need people to start tackling concave up or concave down. Michelle, calling someone.
A? Oh, is that concave up?
It's not Jeopardy. Say it. It is concave up. Okay? That's definitely concave up. It's bending upward. Okay? If rain were to fall, it would collect in the bottom of this cup. Okay? Calling someone, Danny.
Say B.
What do you got?
What is concave down?
No, it is not Jeopardy. What is it?
Concave down.
You sure?
Yes.
Are you positive?
Do you want me to change it?
No, it's
Concave down.
it's concave up.
Concave up.
It's smiling.
Oh.
It's not right.
The cup concave up.
Get it?
Right.
Alright.
All right. So it is concave up.
Do I have a chance to redeem this?
Sure. So again, if the rain were falling, it would collect in the bottom of this. I'm not saying it wouldn't drop out, but it would collect in the bottom of this. Okay? Go ahead. What do you want?
D. Concave down.
Definitely. Concave down. D, concave down is a frown. It rhymes. D is half of a frown. And if the rain were to fall, it would all slide off. It would all shed. Okay? It would be... Yeah, never mind. All right, go ahead, Elizabeth.
C is concave.
All right, good.
Question.
Yep.
I'm sure this is about to the paradox of survive, but how can it be increasing and be concave down, have to be supposed to be decreasing, and it can still be concave up?
Say that again.
Okay.
So I think I know what you're saying, and let me try. Let me.
In B.
Okay, in B.
Decreasing, but it's still concave up.
No, actually, here's the thing, and this is a very common. You guys have to stop. Keith, you have to stop. You have to make sure this is a very common misconception. Decreasing and negative aren't the same thing. In B, it's true that the slope is negative. Okay? That's definitely true. The slope here is maybe -4. The slope here is maybe -2. The slope here is maybe -1. But the slope is increasing. Why does it say what? Because the function is decreasing and the function is concave up. When we talk about these statements, we're talking about what's true about the picture that we see or the function, which is different about talking about what the slope's doing. So it's actually what the slope does that tells us what the function is. And I'll be honest, many students confuse negative and decreasing. They're two different things. And it also gets confusing when you're talking about what the slope's doing and what the function is doing. That's why I try not to say it. I try to use words. All right? Yeah, it can be confusing. Danny, stretching or question? Okay. Tom? Question? No? All right. You want to ask a question, or can we take a look at another problem or two? Michelle's giving me the nod. All right. Yeah. All right. All right. Thank you all very much. Enjoy the rest of your visit. Sorry. While it's opening. Keith, move up. There. I'm not saying it's your fault, but obviously this triangle does not work well together. I would actually say it doesn't work, Travis, to the point where it was somewhat embarrassing to me and to the class. Like that was pretty much unacceptable as far as I can tell. Let me try again. All right. We have that. We don't want that. We have that. We don't need that. We need this. And we need this, this, and this. I don't think your classwork wants to open today.
That's perfectly. Just saying.
I would have thought that you would like it, rather than having to take like copious notes.
Well, I mean, I might not be saying that's in the class, but it's still, I can't see. I know influence. Sure.
All right. All right, let's take a look at 17. It asks us to actually know a little bit about functions, and then comment on concavity about those functions. So we have a true or false going. We have A, B, C, D, and E, and you can pick any letter you want, and tell me if we're going to go A, B, C, true or false. All right. What do you have, Monty? What do you want to try? All right. A. The graph of the absolute value function. So we need to know what that looks like. Do you remember what that looks like? Not a parabola. Close. Okay. A V. Hold on. Whoops. What do you say? True or false? Is the V concave up? Does it bend upward?
No.
It actually doesn't bend. It would catch water, but it